Okay, welcome everybody to this Smart Crete community of practice for asset management. My name's Gavin Chadwell. I'm the chair of this community of practice. Very excited today to hear about a project that the Smart CRC are undertaking on embedded sensing systems for continuous crack monitoring in concrete pavements. Got two very good speakers I'm looking forward to hearing from to update us on the project. Just a little bit of housekeeping for today. Could I ask that everybody, unless you're speaking, everybody keeps their microphone on mute to minimize background noise for when the speakers are presenting. Questions we will keep to, so both presenters will present, and then we'll have a question and answer session after that. So if you could keep all your questions until then. Please use the chat if you have any questions that crop up during the presentation, and I'll read those through after all the presentations. So without further ado, the topic today is embedded sensing systems for continuous crack monitoring in concrete pavements. Concrete pavements are designed to perform well under heavy traffic loads and harsh environments such as temperature changes, wet conditions, heavy loads, and impacts. However, like all assets, concrete pavements tend to deteriorate over time due to traffic and environmental factors. Macquarie University, in partnership with Western Sydney University and Transport for New South Wales, are developing a sensory system for plain concrete pavements. The system will include strain, moisture, temperature, pH sensors that will be placed at regular intervals within the concrete pavements for long-term continuous monitoring of those pavements and cracks in real time. The sensors have the potential to reduce costs for Transport for New South Wales and the public by enhancing maintenance planning through condition assessments of pavements. So topic close to my heart, IoT of things for monitoring assets, and a very specific application and difficult application of embedded sensors within concrete. So I'm looking forward to seeing how the guys are overcoming those challenges. So our first speaker is Hossein Asadi. Hussein has more than 20 years experience in pavements and asset management and materials engineering. He has managed and supervised national and international road and infrastructure schemes on projects up to $500 million. He is currently a senior pavements manager and leads the pavements unit in Transport for New South Wales's Advanced Technical Services. Please welcome Hussein. Over to you, Hussein.
Thanks, Gavin. Yeah, I would share my screen and we can start from there. Okay.
Good, I can see that, Hussein.
Yeah, thanks for the introduction, Gavin. As you mentioned, I'm Senior Manager Pavements. I'm working now in Technical Design and Engineering branch in Transport for New South Wales. The topic is about embedded system for continuous crack monitoring in concrete pavements. But I would like actually to touch base on the background of this project, what happened that, we actually initiated this project. And then later on, I will hand over to Mohsen to talk about technical aspects of this project. But before I start, so on behalf of Transport and myself, I would like actually to mention that we pay our respects to elders, past and present, and recognize and celebrate the diversity of Aboriginal people and their ongoing cultures and connections to the lands and waters of New South Wales. What I would like actually to cover in this presentation is a project overview and the reflection on my past experience that I had in 2012 and motivations for embedded sensor approach and some a little bit on technology and innovation and a brief research methodology and key achievements and what are the next steps. So The title of the project is SmartCrete CRC's R1P48, and it is, as mentioned before, embedded systems for continuous crack monitoring in concrete pavements, which Macquarie University is the lead research organization. And as you mentioned, Gavin, there are some helps from Western Sydney University here as well. But we are also, as Transport for New South Wales, we are lead industry partner. And the objective is to develop a cost-effective, real-time embedded sensor system for crack detection in concrete pavements. So now I would like actually to touch base on what happened that we initiated this project in 2012. As part of my PhD study, there was an opportunity to do some instrumentation in Great Eastern Highway, which is located in Perth, Western Australia. And the main intention of that was like informing our finite element model that was developed by another PhD student on that time for flexible pavements initially. So that was a calibration of the finite element method. And we installed pressure plates, strain gauges, and moisture sensors, and some thermocouples. And you can see a schematic diagram of all the sensors installed in different layers of the pavement. So which you can see, that's a flexible pavement, including lots of asphalt layers together with some limestone granular material. In different colors, are representative of different sensors types. And the aim was also apart from a calibration of finite element method, was also link the lab models, which I was responsible for, to field behavior. And my main focus was on fatigue performance of the asphalt materials, which I was actually doing 4-point bending testing on asphalt, plus lots of dynamic modulus testing in equipment which is called asphalt mix performance tester. And there was an opportunity to use these information captured from the sensors to actually inform the models. But it didn't work very well as we expected. And the issues that we actually faced on this particular instrumentation was it was the system was prone to failure due to rain, repetitive traffic, and unfiltered noise. So when the heavy truck passing an adjacent lane, there was a noise on strain and stress sensors, which we couldn't actually filter that. And also moisture and thermal variations also impacted on the strain and stress accuracy. So there were unreliable information, and to be honest, we couldn't make use of majority of the information captured by stress and strain gauges. The only thing that we could actually be able to successfully capture was, I think, 6 months worth of temperature information, which was helpful, but not necessarily desirable. And the other problem that we had was after a rain event, the entire setup that was responsible to extract the information from field was soaked in the water, and it resulted to degradation of the entire system. But that was not good, but it actually taught lots of lessons to us that what we can do to resolve these issues, and we have learned the lessons. And that resulted us in transport later on in 2000. I guess when we started this project, I think 6 months before starting this project, it resulted actually developing a proposal, or asking Macquarie University to develop a proposal for a better system. This was to ensure that we have the sensors protected in a concrete matrix, and once we actually protect that in concrete matrix, given the harsher situation of the concrete material, then we can in future we could probably be able to deploy that to flexible pavements with asphalt, which might be easier, I guess, if we could successfully embed the sensors in concrete pavements. And the most important thing to me, to be able to actually make use of the data was first of all, given the lots of noise involved in my previous experience with the embedded sensor system was to improve the signal quality and making sure that we are filtering undesirable noise. And the other important aspect of the system is just, you don't leave the system there, for 2 months, and then you couldn't actually capture the information. So with this research, we are aiming to make sure we can continuously monitor the strain and stress and temperature and the moisture variations and pH actually variation as well in different depths of the concrete pavement base course. And that was the aim and motivation to start or embark on this study. So what's involved in terms of the technology innovation in this project? In general, we're going to have 3D printed piezo resistive sensors, which uses the conductive thermoplastic polyurethane, which is called TPU, and that's going to be embedded in concrete together with moisture and temperature sensors, which enables crack detection. We know that the cracking in concrete pavement is influenced by temperature, moisture regime, and also pH differences as well, plus the traffic movement. Depending on how heavy your traffic is, it could actually impact your crack performance. And we are going to have wireless data transmission with real-time cloud dashboard. And we always these days hear about the artificial intelligence, and that's going to have integration with AI for pattern recognition. We can make use of AI these days, to predict, cracking patterns as well. So a little bit about methodology and the achievements so far. What we have done so far, we have done some strain analysis under 4-point bending. It started with 4-point bending testing in the lab in Macquarie University. And we have sensing system developed to integrate the strain, moisture, and temperature sensors within concrete, including a wireless system. We have done lots of experiments in the lab, making sure that the parameters that we are extracting make sense, in terms of the engineering parameters. And I think that's been successfully done by Macquarie University. And that also is useful to calibrate, the sensors in terms of theoretical and experimental data. And we have done lots of finite element assessment, and all these laboratory investigations would also inform finite element assessment to calibrate that model. And finite element is very useful in just reducing the scope of further laboratory testing. And it's a very strong tool once it is calibrated and it's validated. And finally, an AI-assisted anomaly detection using artificial neural network has been developed, which actually uses this technology to reduce the noise, which has been successfully done, and we have actually done it in this project. I think Mohsen can touch base more on the technical aspects of this project, but what's going to be the next step as part of this project is going to be using machine learning techniques for crack prediction. And when you develop a software, typically you would expect you would have a user-friendly graphical interface, and that's going to be part of the next steps. And hopefully we could find a potential location in one of our assets in transport that in future we could be able to trial this technology in our assets, specifically in concrete pavements. I will now hand over to Mohsen, and thank you for listening. I'm more than happy to take any questions at the end of this presentation. Thank you so much.
Thank you, Hossein. Very good overview of the project and some really difficult challenges you're dealing with there. Sensor technology, use of AI, turning all of that information into actionable insights. As I say, bitten off a very interesting project and some difficult challenges there. Good. So our next speaker is Professor Mohsen Assadnia. Professor Mosen completed his PhD at Nanyang Technological University in Singapore, where he focused on developing biometric microsensors for healthcare and robotics. He subsequently joined MIT in the States Smart Center as a postdoctoral researcher, where he worked on developing advanced artificial auditory hair cell sensors. At the University of Western Australia, he held the position of assistant professor, responsible for the development of cutting-edge transistor-based chemical sensors for use in the oil and gas industries. Professor Asadnia is currently a biomedical and mechatronics engineer at the School of Engineering at Macquarie University. Hand over to Mosen.
Thank you very much. Let me just quickly share my slides. Can you see the slides?
Yes, I can.
Okay, brilliant. Thank you very much, everyone. It's a pleasure to be here today and talking with you about our activities and research with transport for NSW and smart grid. So my name is Mohsen Asadnia. I'm a professor at the School of Engineering at Macquarie University. And a lot of research that we do at my team are related to sensors and mainly about the physical sensors and chemical sensors with applications all over the industry, including robotics or wearable devices or even chemical sensors for water quality monitoring or biomedical sensors. So we do a lot of work related to sensors, and what we try to do is, in many cases, we try to develop sensors that are not easily available off the shelf. So if anything available off the shelf, we obviously try to use that, but for those technologies and industries who are required a more advanced sensing system, we try to fabricate those sensors. And another thing that is rather unique about our group at Macquarie University is that we try to not only make the sensors, but also the whole system, including the whole Internet of Things or data acquisition systems and the until the end application. So transitional research basically, and looking at the demand on the market and on industry is primarily our focus and our group. Having said that, during the past around 3 years, we've had the pleasure to work with Transport for NSW on a very, very unique opportunity and project for us. It was basically facilitated by Smart Grid CRCs. So we have been working with the smart and very, very knowledgeable experts in transport for NSW to basically, as Hussein mentioned, develop sensors that are able to be embedded in concrete pavements and monitor cracks, basically. So what we are interested to do is that instead of crack being exposed to the surface and becoming a risk to publics and everyone, we want to monitor the cracks before they even start. We want to see the cracks from inside the concrete. When the micro cracks start to form, we want to be able to monitor them. We want to do the preventive maintenance. And as a result, we want to save money. So right now, all the conceals and transport are spending millions of dollars on repairing the roads and repairing those pavement structures that are exposed to crack. And we have all seen the signs, as I've shown on these slides, that something is under repair, which actually is a good one, because if these repair are not done on time, we have all seen that what are the consequences. We have all had our tires punctured as a result of potholes on the road. Or very recently, one of my lab mates actually was riding his bike and dropping one of those potholes and had to be in hospital for 2 weeks. So we don't want that happen. The whole idea of this project is to keep the community safe as well as save the big chunk of money that is going to preventive maintenance of this structure. Now, as Hussein mentioned, degradation happen in concrete pavements. We have large vehicles passing, and as we have more traffic, particularly in Sydney and in our road, and aging the infrastructure that we have, the challenge with that we have with the pavements and cracks is more and more visible. Australian government is spending about 8.3 billion on maintaining and renewing the roads estates. And that money, we, as mentioned, we try to spend it in a better way by doing a more effective preventive maintenance. So right now, our focus for this project is on pavements, but such technologies and such sensors could be used on other structures as well, on buildings, on bridges, and all the other type of concrete pavements. It could be implemented. So you can imagine that if we have the technology that works effectively, it can have many applications. Now, during the past 3 years, we have been working on developing the sensors, but we have different types of cracks, and each of which requires a bit of fundamental understanding on what type of sensors needs to be prepared and fabricated for what kind of cracks. So build of cracks is a primary civil engineering problems, and they had a lot of like background and fundamentals into it that I'm not going to go through it, but just for everyone to know that we have various types of cracks, and there are different reasons for creation of these cracks. So we have basically longitudinal cracks that can be mainly generated because of the heavy traffic loads, and transversal cracks that are often caused by thermal expansion and contraction. So what it gives us is that it's not only about how heavy is the vehicle that pass through the road or how much traffic we have, but also the weather conditions. Right now we are seeing the severe heat in summers, and then the rains that we have, and all those and the conditions and environmental conditions affect the cracks as well. So we have thermal cracks, we have cracks that are primarily created because of chemical reactions, we have fatigue cracks, and so on, that needed to be carefully looked at prior that we are starting this project. Now, there are different ways that we can monitor the crack. So one could say that, okay, we can have a drone and we can do the imaging of the roads and find out where the crack is, which is a little bit more traditional way. But the problem with that is that crack is already formed as if on the surface when you can see it. It's almost too late, because the maintaining and removing that crack is going to be more expensive, and also as the crack form and water and then rain goes through it and it goes to different environmental changes, the cracks expands and grows very quickly. So we want to do it prior to that. But when we're talking about sensors and embedded sensors, fiber optic sensors are primarily can be used for crack detection, and they have been used. One of the research group at Macquarie University, they are developing fiber optic sensors for corrosion detections and chemical reactions, and also physical changes in concrete, and they are doing fantastic work. We also have fiber crack rating sensors, and we have MEMS sensors in particular, so micro strain sensors that could be embedded inside the concrete and detect the crack, which we decided to work on these type of sensors primarily because they are inexpensive, easier to fabricate, they are simpler to install them, and we get a higher sensitivity from them. And also they can be incorporated with other type of sensors. So as mentioned, strain is one factor, but we have temperature, we have moisture, and we have pH. So all type of these sensors should be embedded in the concrete in order for us to have an effective model of the crack. So when we're talking about the temperature sensors and any of those sensors that I just mentioned for that matter, we always try to use the off-the-shelf sensors as much as possible. The reason for that is that we are talking about hundreds of kilometers of roads, and anything that is off the shelf, as much as we can use them, are going to be less expensive and easier for us to use. And note that for a project like that, it's not only about the sensors, but it's also all about the combination of the sensor data acquisition, getting the data, processing the data. So there are a lot of different components and parts into it. So temperature sensor particularly was one of those that we were hoping to get the commercially available sensors. And to a great extent that works, but the problem is that a lot of temperature sensors have larger size. And in here, we wanted to use the sensors that is the size is the whole system is below 2 centimeters. So while off-the-shelf sensors did a good job for temperature sensors, we also went away and make our own sensors, 3D printed temperature sensors. As you can see, one of them in this image. We fabricated these 3D printed sensors and we tested them for various temperature from 10 degrees to about 70 degrees. And we see that how the temperature performance change. And these are basically resistive sensors. They are sensitive to resistance. As the temperature changes, the resistance of the sensor changes, and we can correlate the resistance change to temperature. So more experiments are done. So in any experiments that we do, we have to repeat the experiment multiple times. We have to make sure that the sensors go back to the initial condition after we have the sensors, the temperature increased, and they can also, when also temperature reduces, it goes back to pretty much the same point. So reliability of the sensors are extremely important, no matter what type of them. And remember, when we're talking about design of the sensor, we need to make sure that they can be embedded inside the concrete and they can work for years inside the pavement. We don't want to be needing to dig them up and then change them every so on then. So material selection has been extremely important to get a reliable sensors. The power consumption of the sensors is important. You don't want to be needing to change the battery every day. So that's why we try to use the self-powered sensors as much as possible. So most of those challenges need to be carefully considered. As Hossein said, finite element simulation has been a very, very instrumental tool for us in this project. That allows us to, instead of doing a lot of experiments by multi-physics simulator techniques, allows us to see that what is the best way to design the sensors. We can have the pavement, we can have our sensors in there in the simulator, and we can see that when the truck passes by, how much force it applies, then we can select the materials in a way that the sensors can actually measure that or bear that. And so simulations are great ways for us to give us the data without the need to run the experiments. And we do it in all aspects of the project. Let's say we want to know where to put those sensors. Should we put it on the center? Should we put it at the bottom or at the top? How many sensors do we need in 1 kilometer of the road? So all of it we can run through simulation first, get the information, and then we can implement those findings in our experimental works. That saves us a lot of energy and time. Now, we come up with various types of sensors. Through this project, we came up with at least 8 types of strain sensors. So some of them were not effective. Some of them were just tested, and we realized that, okay, they are not probably working there as long time as we want. Some of them are not as repeatable results that we wanted. Well, we come up with piezoelectric sensors, capacitive sensors, and piezoresistive sensors. So piezoelectric sensors basically work just like the automatic watch that you have. You move them to generate voltage, and that voltage can run a mechanical system such as your watch. So they are powerless, so such as quartz. So we use those smart materials, and when we apply the strain to it, the voltage that is generated can be read, and we can calibrate it against the stress that is applied to the sensor. Piezoresistive sensors, on the other hand, they require power supply, but they will be very accurate, and you can monitor the resistance change. And capacitance sensors, as you can imagine, they work based on change of the capacitance on the sensor. So there are different types of principles. You all learn about them in high school physics, but you can see that there's a realistic applications of all those fundamentals in this interesting project. Now, what you see here is the experimental setup that is we have put together, and it's a standard experimental setup that is used for running such experiments. So you can see a slab here, and this can be made in different sizes. Usually they are about 100 millimeter at 100 millimeter is the surface, and we have 400 millimeter of length, and we call it a 4-point bending because it has 4 points, as you can imagine, and then it's connected to a pressure device that you can apply a pressure here. And as this part of it goes down, you can imagine that there will be a crack exactly at this point, and that's exactly what we want. We want to have our sensors in the slab, then we want to be able to create the crack. We want to apply the force that we want, stimulate the crack, and we want to monitor the sensor performance. Now, if you're sure that your crack is going to be in this point at the middle of the your 4-point bending, then you can validate your simulation. We can have our sensors across the crack, like we can have one sensor here, another sensor here, another sensor here. We can have the sensors in different distance from the source of the crack, and then we can monitor how the sensor perform, how effectively they can detect the crack. Basically, we can answer to this question: how far sensors should be away from each other in order to effectively measure the crack. So having done that, you can see that the results in here, we have 4 sensors. The sensors that is closer to the source of the crack will give you the maximum signal as the stress is applied, force in this case is increasing, and then there is a crack. You can see that the crack is formed here, and the other sensors which are further away from the so like these sensors that are further away from the crack, they have lower signal. So repeating this experiment for multiple times, and also for different locations. As you can see, crack is formed here now, crack is formed here, a crack is formed in the center, will give us an exact information on how the sensor basically perform on their different forces, on their different locations of the crack, and then accordingly we can monitor the crack. And then we can see that if the sensor is effective or not, and also we can validate our simulation results. Now, here is another sensor. This is a piezoelectric sensor. As you can see, as mentioned, it's a self-powered sensor, and this is based on PZT ceramic. We use various types of the thickness of these sensors, and then sorry, just a little bit going back to the slides. Okay, and then here is the UTM machine, our 4-point bending that I showed you. And then the sensors are at this stage still wired to the computer, because we are interested to see that the sensor output only here, but at later stage we make the whole system wireless. So here you can see that the sensor output and also displacement of the UTM machine, when we have various types of forces applied to the sensors. And in here, we can see the other characterizations such as load rates and the peak-to-peak sensor output. So a lot of characterization and different stage when different form is done, just to ensure that the sensors are performing well the way that we want. And if not, then they will be either changing design on the sensor, changing materials, or a completely new type of sensors will be introduced. What is important for us is that through signal processing and through basically big data modeling and artificial intelligence, we can get the early signals of crack. And what it means is that we can get a signal before even the crack form. We can know that there is a risk of having a crack at certain part of the slab. And that's pretty much what we want through this experiment. So here we can see that when the up to 600 second the experiment is done, at some stage we have a change in shape of the signal, which is a warning signal that there could be a crack forming here. And at this stage now we are trying to look into it. So looking at different type of shape, their formations, and their magnitude, we can get really interesting information about the crack. Now, here is one of the design of the sensors that now is actually going to be used in the field. We have piezoelectric sensors, and we have this flexible design of TPU that is forming a flexible package of the sensors. And this package, as you can imagine, concrete, particularly when it's already when it's early pure, is not really the best environment that electronic device would like to work at. They are exposed to temperature as the concrete start to cure, and also water and moisture could go to electronic part. And as it solidifies, it may affect most of the electronic devices. So the packaging was really important for us. We needed to be very careful how do we package the sensors in order for them to work. And also the location, the positions of the sensors, how do we fix the sensors and then pure the concrete. So all of them were aspects of the projects that the team has been working very hard on that. So here you can see some other results that we have after 800 seconds. We can see that the early signs of the crack has been formed for these sensors, and that's kind of give us the indications of the crack. Now, moving forward, you can see that another big challenge that we had with this work was wireless communication. When you have tens of sensors in the pavements, including temperature sensors and moisture sensors and tactile sensors, you definitely don't want to have all those wires coming out. The requirement that was identified by Transport for NSW correctly for this project was that you should not be able to see anything on the surface of the concrete. There shouldn't be any wire, no data coming through any kind of hardwares outside the pavement. And ideally, we want to be able to get the data on cloud. So we are sitting in our office, we're running our data processing algorithm, and the data will come to it, and the measurement is done. So we want to do with as minimum as manpower as possible. Now, something that we have come up with here, we can see that we have multiple sensors. We have connected it to the data acquisition wirelessly. And as you touch each sensor, every sensor give you a peak, a signal. Like when you touch a few times this sensor only this sensor will give you a peak. And these are the other sensors don't have any distinguished performance. So wireless communication has been working really well. And I guess the next step for this project at this stage is to have the field experiments, have the sensors on like 100 meter or 1 kilometer, and then run them different equipment with it and machineries on it, and observe the crack. The other important factor that we want to do for future work is as briefly mentioned, is the data, is artificial intelligence and data processing, because you can imagine that it's a continuous monitoring, day and night, 24 hours. You're collecting the data, and you need those data to be able to monitor the crack across the roads. And so processing all those data is very important. And this is something that we are working on that. And also we are keep working on the technology itself and making it better and better and better. There's no end on how good the technology should be to have a reliable mechanism that works for years inside the concrete pavement. I should thank I don't have the image of Dr. Sajjad Mushizi, the postdoc who has been working on this project tirelessly. He has done most of the work that I presented here. Also, Kaveh and Jenny are two PhD students that are working on this project. So it's a teamwork together from Macquarie University, SmartCrete, CRC, and particularly experts and colleagues from Transport for NSW who help us do this project. Thank you to all of them. And thank you to you. I'm happy to answer any question.
Thank you, Mohsen, and thank you to Hussein as well for your presentation. Now open it up to the floor for questions. So if you have a question, could you use the raise your hand feature on Teams, and then we'll call you out. Just introduce yourself and ask the question. If you don't want to speak up, then please just put your question into the chat, and I'll read that out. But to kick things off, I've got a few questions as well. Maybe first one for Hossein. So I'm no expert in pavements, but my understanding of how things are traditionally done in terms of modelling and assessing end of life for structures, there's or pavements, there is a modelling component where you assess assumed axle loads over a life, and you get a structural life, and then you get I suppose a visual assessment based on surface defects, and you collate those two, and you come up with you do clever pavement engineering stuff, and you come up with either maintenance or replacement and the rest of it. Just wondering how this technology would feed into that, or possibly replace it, or how it enhance it.
Yeah, I think that's a really good question, Gavin. It just not traditionally, it's also a complex issue to resolve. Like, it's called pavement management system. I think that pavement management system is also one of the most complex, I think, problems to resolve, because you have limited budget all the time, and you have limited probably just equipment to capture the information. But we have also lots of innovations in data space. But to me, that methodology is more reactive to like being proactive in terms of detecting the issues within the pavement. So if we can actually combine this technology with the existing technology, which typically involves a network surveying vehicle to go around your pavements and capture information about your not necessarily concrete pavements, it actually could include other pavement types as well, which is probably rotting, cracking, and all other problems that you can capture network level. Then, when it comes to the project level, because it depends, which way we want to go in this particular project. If we can actually put the sensors everywhere in our network, or we can actually have limitations in project level. These are all complexities that we need to decide. But I think the future would tell us that whether we can replace the existing technology with the sensors, because I think, to me, there's a lot of potential being I think detecting the issues in pavements before it starts to happen. But the current technology that we have is, as I said, it's more reactive, because the issue has happened, you're capturing the information.
So it'll be in combination, but it's a significant enhancement.
Right. I think in the future would tell us, but I think there's a great potential in this technology once it's been trialed, because we are in, to me, we are still in infancy stage. So we have to be able to deploy it into our like existing pavements, and then start actually expanding on that. I'm really hopeful on that, because as I said, in the beginning, I had lots of issues with the systems, like sensing systems, and now we have overcome like those problems. Now it's at the stage that we can trial it and probably expand the scope in future.
Yeah. Okay. Thank you, Hussein. I think we've got a question from Bador. I hope I've pronounced your name correctly.
Yes, this is Bahadur. That's fine. Yes, you did very well. Thank you very much, Hussein and Mohsen. I was really glad to be in this meeting and listening to those presentations. It is I'm leading one project with the smart grid for just utilizing fiber optic sensing for rail monitoring through the concrete sleepers. And I see how those two projects, your project and our project, is exactly like one project in a couple of steps. Through fiber optic sensing, we wanted to look at the whole railway. Along the railway, just like billion and billion sensors we are applying to the railway. But what you are doing is giving us the exact just conclusion and outcome of censoring in one point. My question is, how just you detect the more vulnerable just section of your asset to see if that's the best position to test the sensors? And then that's the reason I'm asking this question, is because that facilitate our project to see where we have to just focus more on the railway, because on the railway, like roadway, just we've got the bridges, we've got tunnels, we've got curves, we've got the straight line and uphill, downhill. That may help us a lot. And I hope I get the chance to connect with you guys directly and see how we can work together. Yes,
Yeah, I
please.
can probably start on that, and Mohsen, you can probably add on that. Typically, from pavement point of view, you would probably need to focus if you want to actually just go with the problematic areas. Like, if you want to actually say, okay, I'm going to actually select an area that's problematic. Probably you need to focus on your support condition. So if your support condition is weak, for example, you have weak subgrade, or weak formation in your rail, probably formation. And in areas that with harsher environmental situation, there are lots of rain there, probably like pH differences, specifically in concrete environment, plus the traffic. Traffic for us is different, but in rail might be same. Like you may have, I don't know, like, because rail, it depends on how many times the rail passes that section. So you may need to focus on those aspects. But is also a bit difference between rail sleepers and concrete pavement, because concrete pavement is like designed in a continuous kind of arrangement with lots of joints. But sleepers, typically, unless you have a tracker slab, it's different scenario. But if you're focusing on only on sleepers, like concrete sleep, they're actually like their distances with ballasted formation. So in terms of shrinkage forces and all these things, you may have better environment than concrete pavements. Because if the concrete shrinks or expands in our environment, it may actually have lots of other damages on the structure of the pavement too. So we I think in that aspect, we are also in the harsher side. We can probably discuss offline if you want to connect and just go through your project, and I could probably just help you on that aspect in my free time.
Yeah,
Thank you. Yes, I
think
appreciate that. Sure.
just on that, Natalie could hook you up with emails and all the rest of it.
Yeah.
So if you wanted to continue the discussion online, I've just seen there's a question in the chat for Mohsen from Subra Maji. The question is, or it's in three parts by the looks of things. The piezo resistive sensor is of a certain topology. Any reason for this topology? The piezoelectric sensor, was it actuated with an electrical pulse or operated in a passive mode? Was the received signal amplified, and are the wireless sensors connected to a hub locally with a wire that transmits the data wirelessly to a dashboard? So quite a bit in that, Mohsen.
Yeah, that's exactly right. So the first one, the piezoresistive sensors are designed in different shapes and materials just to get the better performance out of them. So both materials and shape was optimized through the mainly finite element simulation and then experiments to just get the best response. And also it's not only sensitivity from the sensors, the durability and the materials that we use is very important as well. We don't, as mentioned, we don't want to use volatile materials that can only sensors can work in the concrete for only a few days or a few months. It needs to be prolonged number of years that works in it. So we haven't done that. We haven't gone through and see how many years it works. But in theory, we need to make sure that the packaging and the sensors work for a very long time. In terms of the wireless communication, all the sensors are internally wires and they're connected to a hub every 8 sensors at the moment. And then through that hub, the sensor output will be sent out to cloud. But everything is inside the concrete, so there is nothing outside. We don't have antenna and everything. So the antenna and the design of the wireless communication was a big part of the project that's still ongoing. So on surface, you don't see any wires or any antennas. I forgot the second question. It was
yeah, the second question was the piezoelectric sensor. Was it actuated with an electrical pulse or operated in a passive
it wasn't. No, it operated in passive mode. Remember, we don't have an amplifier as well in here, and primarily because we want to reduce the power supply as much as possible. If we add amplifier or filter, filter to a good extent we have added, but anything that requires extra power, we avoid. So the simplest, and also the size is very important as well. So the project, the main challenges is because of the power, because of the size and durability of the device, and that's why when you go in depth of the project, you will find a lot of challenges to overcome.
Yeah, got a follow-up question to that, Mohsen. Is that the hardware you've got lots of challenges there and quite sophisticated, but some of those graphs you showed, there seems to be or the potential to generate lots of data, particularly if you've got multiple sensors along a stretch of highway. How are you dealing with that volume of information and analyzing that? Could you tell us a little bit more about, it's almost like drinking from a hose pipe. It's too much data and you can't see the wood for the trees. So
that's exactly right. That's exactly right. And that's mainly for the future work of the project. Right now, our challenge has been to get the sensors working, the wireless communication, get the data to cloud. And now what Sajjad is, the postdocs on the project is working, is to design the AI algorithm to look at the shapes and magnitude of the signal. So the way that we are going to tackle it is that we're going to have a lot of data that is coming in, but we are designing an algorithm that look at the signals and just pick those shapes that we have defined and algorithm is trained for. So not all the picks are interesting for us. We are also getting signals. For instance, if a car passes by, we get a peak, but that peak is different by the peak.
Project around concrete pavements potentially could have application to flexible pavements. So sort of see potential to use this as you mentioned in your presentation for other monitoring of other concrete structures. Broadly speaking, I sort of see this as it's monitoring in situ performance of concrete structures in the broadest sense under load. Have you started to think about how you could potentially use this in other structures and using it from day one in installation, where things that you might be interested in might be around thermal performance of the concrete as it's being poured through to, and those uses may change, or the information you're interested in changes from through pouring the concrete, through construction strength gain, through to asset life performance. So just interested to both your thoughts just on that. Appreciate it's going off track from the pavements.
No worries. No, maybe I give a bit of
شما
discussion and then Hossein can continue.
Yeah, I can probably just
yeah,
mention
sure.
something before. So like it's not the sensors are not like this, you wait for the concrete to actually just 28 days it's like hardened concrete. It starts from the day one. It captures all the information from the day one. Once you have poured the concrete and it's been just hardened after 28 days of finishing the hydration process. So it gives you the information, because it is important to capture all this information like temperature, pH differences once you're pouring it. And some of the issues with the concrete relates to early stage of the concrete hydration, specifically like drying, shrinkage, and all these things. So it is important to capture all the information. To me, if this is going to work for concrete pavements, it could be work very well with other structures, because they're using concrete too. Depending on it, the only difference would be like the loads might be different, might be like they're suffering more from static loads rather than dynamic loads, or moving loads that I think they're more complex than the static loads to observe. So I will probably hand over to Mohsen to explain more.
That's exactly right. That's exactly what I had in mind as well, Hossein. I think you covered it very nicely. The next things that I would add to what Hossein said is that we need to work on the reinforced concrete pavement as well, to see where to put the sensors. So that I would say that there are two categories. Another category that we need to look into, and we have one student working into it, is when we have reinforced pavements. So having a look into that from the beginning, from the get-go on day one, when we pour the concrete, and looking at the sensor performance will give us a better ideas, and then we can expand it to different concrete structure.
Good. Look, we're bang on 1:30, so I'll draw everything to a close there. I'd like to thank Hossein and Mohsen for their very enlightening presentations. Doing some great work, guys. Keep it up. Look, I appreciate we've not had much time for questions. Maybe if there's anything burning that you have that we haven't covered off, maybe send that to Natalie or Bador as well. I think Natalie can hook you up if you want to follow up discussion. So yeah, I'd probably leave that with Natalie, give her a little bit of homework there. If anybody wants to reach out to the speakers or myself, just go via Natalie. But thank you both again, and thanks everybody for attending. Thank you.
Thank you.
Thank you.
Thanks, guys. Bye.